Hi, welcome to the 𝑣𝑒𝑟_STE mathematical statistical problem solving section. So today, let's take a look at how to solve some hypothesis testing problem here. So, and the problem we're going to work today is a very basic hypothesis testing. We're going to take a look what is the most powerful test and what is the power of the most powerful test. See here. Okay, so this problem, like I mentioned, is a very, very basic problem for the hypothesis testing. So, okay, let's take a look. We said consider the sampling from the parent function, the f of x theta is equal to the theta x theta minus 1, x range from 0 to 1, the parameter theta greater than 0. So now the random sample right now, we only have size n equal to 1, x1 from this parent population. So we want to find is what is the power of the most powerful test for the non-hypothesis theta equal to 1 and alternative hypothesis theta equal to 2. And the type 1 error, we define alpha to be the 0.05. Okay, so now let's go ahead, go to the whiteboard, and let's take a look at how we're going to solve this problem here. Okay, so before we start, find the power of the most powerful tests here. So let's kind of let's do a very brief review, and this is the theory we're going to use. We call this is the Newman. So this is a Newman-Pearson. So some people call NP lemma. Okay, so what is the, what is the Pearson NP lemmas here? So we say if we have a non-hypothesis here, is theta equal to some theta 0, and the alternative hypothesis here is theta is equal to theta 1, is for the simple hypothesis test, alternative hypothesis. Okay, so it's a simple here. So it's both equal to specific values here. Okay, so let's say if k is a constant. Okay, so if k is a positive constant, okay, and we know a test, we call it is phi of size alpha. Okay, so with the critical region, C having, so if we do the likelihood, so we say the likelihood function of the theta 0 over the likelihood function of the theta 1. Okay, so if this number is less than this case here, so for the k, for the x in the critical region, okay, and we have a greater than case here for x inside the company, the outside the critical regions here. So now we said this is the most powerful test, okay, to test this hypothesis here. Okay, so let's take a look. From our problem, we also start very simple. We say x theta is equal to the theta x to theta minus 1 here. So now let's take a look based on the NP lemma here. I have x to the theta 0 and the likelihood of x theta to the 1 here. So remember, right? So from the introduction, we said on hypothesis we want to test here. So what is the hypothesis we want to test? We want to test the theta equal to what? we want to test theta equal to 1, and versus the alternative here, theta equal to 2 here. Okay, since we only have a sample size 1, so for the x0s here, so x0 is theta equal to what? Theta equal to 1. So that's why here will be 1 times x theta 1 is 1 minus 1 is 0, right? Then on the bottoms here is alternative hypothesis. So alternative hypothesis is theta equal to 2. So I have a 2, then this x is the 2 minus 1. So if we simplify this a little bit, this is 2 to 2x, correct? And so we say this one is less than what? Is less than some constant k. Okay, so the list is less than some constants k. So if I do a little switch here, I can say that x is greater than what? So I can set x is greater than some k stars here. Okay, so the reason why I say k stars here, so I would say 1 over k is greater than 2k, and so the x is greater than 1 over 2k, right? So I can say this whole thing is some k stars here. So x is greater than k star. So now I know that this one's here based on the NP lemon, so this will be what? This will be the most powerful. This will be the most powerful test rejection regions. Correct? And because the problem tells us alpha is equal to the type 1 error. So here, this is 0.05. That's back. So that means the alpha, that means when null hypothesis is true, and you in the rejection regions here. So when the null hypothesis is true, when the theta equal to 1 is true, my PDF here, x1, right? So it's just equal to 1, right? So that means 0.05 will be equal to what? Will be equal to the hypothesis H0 is true, so my PDF is 1, and my PDF is 1, and then this is dx. And because in here we just say the rejection regions, right? So this is the most powerful rejection regions here. So this is greater than k star. So that means I have some k stars, and the x is from 0 to 1. So to 1 here. I know this one's integration because this is a 0.05. Okay, so now in here, then this one's here. I know this will just be the integration will be just x. Then it's 1 over k star is equal to the 0.05. So that means I can get, so what is the k star? So it's 1 minus k star equal to the 0.05. So that's why I know the k stars here is equal to what? 0.95. Okay, so now that's what I find the rejection regions here. Okay, so now the problems here, I want to find the power. So what is the power defined? Power is from the intro step 101, we know power is when the H0 is a false. And we reject H0, all right? So when the H0 is a false, that means HA is here. We take the HA, so it's theta equal to 2. When theta equal to 2, the PDF here is what? Is 2 to the x, right? Because this is 2 minus 1. So the PDF is 2 to the x here. So that means 2 to the x dx. I'm rejecting rejecting the rejection region is greater than K star. And we just figure out, right? So a while ago, we just calculated the K star equal to the 0.95. So that's why we have a 0.95. The rejection region is 1. It's correct. So this will be a very simple integration, will just be x squared and 1, the 0.95. So now you substitute, and I'm getting the 0.0975. So the power for this test here is 0.0975. So like I said, this is a very, very basic, very, very fundamental type of the testing hypothesis problem. And our next video, we're going to go a little bit more complicated here. Okay, that's it. Hope you enjoyed it, and I hope you get a good understanding how to find the most powerful test and how to find the power of the most powerful test here. And okay, so looking forward to talk to you more in our next videos here. All right, have a good day. Okay, bye-bye.